Joshua Fraser. I'm a product marketing engineer at Texas Instruments. I'm in the power team that covers DC-DC buck regulators. So today we'll focus mostly on what we call mid-voltage buck converters. That would be those targeted at the 5 volt, 12 volts, 19 volts area of input voltages, and then high currents, which we define as 6 amps or greater. And in this case, we'll go over up to 40 amps of current. All right. Great, so today what we want to really focus on is high power density. That's something that a lot of customers in a lot of different markets struggle with, is achieving higher power density. So we'll talk about a couple of different ways that we're designing our buck converters to help solve that challenge. After going over a little bit about the different ways we're doing that, we'll go over some of the top latest products that we've released to the market. Start with these 4 here, and then finally we'll go into some closing remarks. Okay, so a lot of different ways to define power density. The way we define it is essentially is just how much power can you get out of the smallest surface area of a PCB. So, when we're looking at buck converter products, how can you get higher power density? And we've defined today, we're going to talk about 4 different ways: faster switching frequencies, smaller, more advanced packages, multifunction pin capability, so using one pin for multiple functions, and then talk about internal compensation in our different control modes. So starting with faster switching frequencies, so that's one way, is by increasing the DC-DC converter's switching frequency to reduce your inductor area. New devices from TI are being specifically designed to minimize the switching losses and have higher efficiency at a higher switching frequency. In one of the products we'll go over today, as an example, you'll see between 600 kilohertz and 1 megahertz, there's only about a 1% efficiency difference, which is very minimal. So you can switch at a higher switching frequency, achieve smaller solution size by reducing your inductor area while still maintaining good thermal performance. The next area is smaller advanced packages. So in TI, not only do we talk about the converter IC design, but we talk about package design. So we have hot rod products. These are flip chip on lead frame. Compared with traditional QFN packages, there's no wire bonds required. So you have 2 options there. You can either increase your die size inside, and you can get larger FETs and have lower RDS(on) for higher efficiency, or you can reduce the size of your solution since you don't need area, the keep out area for that wire bond. So we see a lot of our newer products moving to a hot rod type package just for their increased power density over a traditional QFN solution. Another package technology that we are investing in is a stacked clip QFN. So what this is it's a package type which has a large single ground pad on the bottom for good thermal dissipation, but also has the low side FET and the high side FET stacked on top of each other. This 3D type of architecture allows for larger FETs since they don't have to be side by side on one ground plane. And because you can have larger FETs now, you can have lower RDS(on) and reduce parasitics. So just another way that we're enabling using a higher Z height to also reduce the XY area on your PCB. All right. Multifunction pin capability. So as buck converters and regulators get smaller and smaller, what you're maybe seeing is, how do we keep the same amount of pins? And in some cases, we can't. So what we have to do is use a multifunction pin capable design where one pin can service several different settings or features of the product. In the example below, what we're showing is this one mode pin via a resistor divider to ground. You can select a current limit, you can select your ramp setting for compensation, and you can also select your soft start time. So all of this done by one pin. So that's just another way to keep the functionality of a product while also reducing the package size and the number of pins overall. Finally, internal compensation. So a lot of our newer products that you'll see that we'll talk about have either an advanced current mode control, which is internally compensated, or a DCAP3 control mode. Versus traditional current mode control, which is externally compensated, you'll see fewer external components. It'll lead to an easier design and less verification. So in the example we're showing here, you'll see there's, on a traditional peak current mode control product, we have 3 external capacitors and 2 resistors to realize compensation. On our new internally compensated advanced current mode control product, we only need 2 resistors to realize the same compensation network. All right. Great, so the first product that we want to talk about today is the 543-620. So this is our highest efficiency 12-volt 6-amp converter, and highest efficiency 12-volt 6-amp converter in the market. So it is, again, internally compensated advanced current mode control, is in a hot rod package, so it doesn't have the wire bonds, and it is selectable switching frequency up to 2.2 megahertz to enable the smaller inductor size. Another way that this product can optimize power density is through its adjustable current limit. So for rails where there is less than 3 amp load conditions, you can actually select the 3 amp current limit and scale your inductor accordingly. So that's just another flexible feature of this product to help enable higher power density in that condition. All right. Over our current generation device, the 54824, the TPS 543-620 new product can offer up to 55% reduction in solution size. And again, that's done through faster switching frequency. You'll see 1 megahertz operation on the new product, over 600 kilohertz of the current gen solution. No loop compensation, so again, 2 resistors instead of 2 resistors and 3 capacitors. A smaller package size, and the mode pin functionality enabling multi-functions through 1 pin. All of this is for the same, if not better, efficiency. So on that efficiency note, we'd like to look here at the 543-620 efficiency versus TPS 54620 and the TPS 54824, which are the current gen solutions which have been used widely across many markets. You'll see at the same switching frequency, 600 kilohertz, with the same inductor, Draco, the TPS 543-620, can offer significant efficiency improvements at full load, 6 amps, as well as at a half load, 3 amp range. As mentioned earlier in the presentation, Draco, the TPS 543-620, is small difference between 600 kilohertz and 1 megahertz. So really designed for high power density, high switching frequency, and small solution size. Okay. The next product we want to discuss is the TPS-M 41615 and the 625. So these are 15 amp and 25 amp pin-to-pin stackable power modules with excellent transient performance. So a power module is another way to get high power density by not just integrating the MOSFETs, but also by integrating other external components such as inductor, input capacitors, and things like that. So the TPS-M 41615 and 625 also use the advanced current mode control architecture. This power module is in a power dense 11 by 16 by 4.2 millimeter package. Some real advantages of this product are its fast transient response. So it has features such as asynchronous pulse injection and body braking, which help to reduce overshoot and undershoot during a transient. This feature can also be enabled or disabled. So depending on your system requirements, you can either enable it or disable it. The other benefit of this module is it's stackable, meaning not necessarily you throw or put one product on top of the other, but that you could parallel the devices and tie their outputs together in current share for up to 50 amps when you stack two of the 25 amp solutions together. Okay. The next product we want to talk about is the TPS 542A52. This is a fixed frequency, internally compensated voltage mode product with current capability up to 15 amps. So one good thermal benefit of this product is it meets T sub A of 95 degrees C up to 14 amps. So very little D rating. 15 amps is the capability of the product for a very high T sub A. This product is also in a hot rod package in a 4 by 4.5 package size, and it switches up to 2 megahertz, again, enabling a small inductor size. Talking about the switching frequency of these products, we have here two examples, one at 1 megahertz, showing 380 millimeters squared solution size, while also showing a 2 megahertz design with even further reduced area on the board at 180 millimeters squared. And so a big driving factor there is the inductor size, small inductor size, less C out, while still, again, meeting T sub A equals 105, high current application. All right. So the final product that I want to talk about is the TPS 546, D24A, B24A, and A24A. So these are a PM bus family scaling from 10 amp all the way up to 40 amps. These all are pin-to-pin with each other. So you can easily scale from 10, 20, 40, depending on your load current requirements. It's stackable by 4. So again, you can parallel the outputs and current share between products, up to 4 of them. So you can get up to, with the 40 amp converter, 160 amps of power out of a small area. These products implement a fixed frequency, again, internally compensated to save on that board space and external components, average current mode control. So these products also have an extensive PM bus command set with output voltage margining, output current and temperature monitoring telemetry feature. So another benefit of a PM bus product like this is you can select different features of the product through PM bus, or again through the multi-pin function M-cell pin. You can use a resistor to ground network to also select different features of the product. Both ways enable reduced pins, reduced output components, and higher power density. This product family here utilizes that 5x7 stack clip QFN package that we discussed earlier that has the 3D architecture, where the high side FET is stacked on top of the low side FET. Again, really low RDS(on) MOSFETs, 5 milliohm and 1.6 milliohm high side, low side MOSFETs in the 20 amp solution. The 40 amp solution has even lower RDS(on). But as an example, with our 20 amp solution, we see an efficiency of greater than 90% at 12 volts in, 1 volt out at 500 kilohertz. Something that you should start to see in a lot of the power products, DC-DC buck converter data sheets for our new products is an SOA performance curve. This shows on the y-axis the ambient temperature, on the x-axis the current capability at different airflows. So at natural convection, no airflow, you're able to see that the TPS546D24A can get 40 amps at 83 degrees C with no airflow. High efficiency, we talked briefly about that already. But in the case of the 40 amp converter, we see a 92% peak efficiency at 15 amps. At a 12 volts in, 1 volt out, 325 kilohertz use case. The final piece on this family I want to mention is we also have a reference design on TI.com, the PMP21814, which shows the small size and stackable feature of the product. So what you see here is 4 40 amp phases, each occupying less than a 1 inch by 1 inch, or I believe a 22.5 by 22.5 millimeter squared area. So it's a good reference design to reference whether you're looking at 1 40 amp design, 2 40 amp designs, or even stacked up to 160 amps. It's a very modular board layout, so it's very easily copy and pasted depending on the number of phases and current capability that you need. Lastly, I want to highlight on this family some of the collateral and tools to help you design with this product. So the first one is an EVM board that shows a stacked 2-phase design, providing up to 80 amps of current. The other is software tools. So we have compensation and pin strap resistor selection spreadsheet, a Digital Fusion Power Design GUI, and PSpice models available for download. We already talked about the TI design, PMP21814, showing the 4-phase stackable design up to 160 amps. So we have on TI.com that BOM, test report, Gerber file, and schematic. We also have other application notes that explain how to use the TPS546D24A in other applications, such as using it from a single 3.3 volts input, or shows you how to achieve better Vout accuracy. Great. Yeah, so that hits on everything that I wanted to discuss today.
Thank you, Josh. Since we have a few minutes, we can open it up to a few questions. So type in your question in the chat. I think there's one or so, and we can answer them on the call. And just a reminder to visit www.ti.com/NPU, and you will get the archived recording of this webinar within the next few hours. And you can also see the schedule for the upcoming webinars. Next week's webinar is Implementing Amazon Sidewalk with TI Connectivity.
I see the chat, so I can start to answer a couple questions there. So I see a question on continuous or discontinuous conduction mode. So the TPS 546D24A operates in forced continuous conduction mode. Then I see another question on 24 volts input, 12 volts output at 10 amps. So for my product category, we typically focus on products on the 5, 12, and 19.5 volts input rails. In TI, we do have a product group focused at 24 volts and higher input voltage ratings. So I believe by searching the TI parametric table, that would be the best way for us to determine what product is best suited for the 12 volts input, or the 24 volts input, 12 volts output at 10 amps. That team may have something on there that could service that rail.
Great. With that, I think there aren't any other questions. Oh, there's another one coming in.
Great. Thank you all for your questions. For the next question, I would also recommend using the TI parametric table. The products that product group that I was just talking about, they cover 12 or 24 volt inputs, and I believe they have products rated all the way up to 100 volts on the input. So in that 24 to 100 volt input range, we do have a team specialized at products in that category. Please take a look at the parametric table. There may be some products on ti.com there that could meet these requests.
Great. Well, thank you, everybody. And please check back on ti.com/NPU later this afternoon for the archived recording. And have a great day. Thank you, Josh.
Great. Thank you.